Welcome to our discussion on statements and quantifiers. This is going to be our introduction to logic. All right, so here are the various kind of topics we're going to cover: statements, negations, symbols, quantifiers, and sets of numbers. Let's start with some vocabulary. A statement is a declarative sentence, right? It's either true or false, but it can't be both at the same time. So when we talk about a statement, we're not using the dictionary definition of a statement, which can be just about anything. We're using the mathematical definition of a statement. So it's something that can be true or false. It can't be opinions. Basically, the sky is blue. That's a declarative statement. Um, Water is solid. Even though that's false, that's still a declarative declarative sentence. Okay, a compound statement is just like it sounds. You're just going to combine two pieces. And if the statements that are making up the compound statement, they're each the component statements. Again, you don't have to worry about a lot of this vocabulary. It's just when you come across it in the book, you understand what they're saying. And then, of course, whenever you have these compound statements, a lot of times you'll have these connecting words: and, or, if, then, not, things like that. All right, let's look at an example. Can we decide whether each of these statements is compound? So if Amanda said it, then it must be true. Can you see how we have two statements here? We have basically Amanda said it, and that's a statement because it can be true or false, but it can't be both, right? Either Amanda said something, so it's true, or she didn't say it and it's false, right? And then if and then are our connectors, and then the other statement is it must be true. Again, whatever it is that she said, must be true is something that can be true or false, but can't be both, right? All right, the gun was made by Smith & Wesson. It's got the and in there, but is it really a compound statement? And it's not, because Smith & Wesson is just a name, right? So this is just one statement, but not a compound statement. Okay, how about this one? Negations. The sentence, Max has a valuable card. That's a statement, right? Because it can be true or not, right? Max has a card that's valuable or it's not. Obviously, they're playing some sort of game with valuable cards. Magic the Gathering, or maybe they're just playing poker. Now, the negation would be that Max does not have a valuable card. Be careful, because the negation would not be Max has a worthless card, right? Or has a card that isn't valuable. That's not really the negation of this. When you negate something, you're negating the verb. You're not normally negating the adjective, right? Valuable describes what kind of card it is. The opposite of valuable is not worthless, because there's an entire spectrum of value, right? It can be really valuable down to worthless. It could be somewhere in between. So you can't negate it by just picking another adjective. It's kind of the idea of complements that we talked about in probability, where these two things have to be the only two options in order for them to be complements, right? And their probabilities would add up to 1. So in this case, the only negation is you have it or you don't have it. So when you're negating things, you're usually looking to negate verbs. Let's remind ourselves of what the inequality signs mean in verbiage, because oftentimes that will help us to negate things, right? So we've got A is less than B, A is greater than B, A is less than or equal to B, and then A is greater than or equal to B. The reason why that is useful is because we can now use that to negate things. The opposite of less than, right, the complement, if you think about the entire spectrum of the relationship between P and 3, it's either less than it, equal to it, or greater than it, right? Those are the only options. So if one statement is that it's less than, the negation has to be everything else. So it's not just greater, it's greater than or equal. It's the idea of complements, right? So greater than or equal to goes to less than. So if you think about it, basically what's going on is you can pair these things up. Less than and greater than or equal to are complements, right? They're negations of each other. And greater than and less than or equal to are negations of each other, complements of each other. Okay, some more symbols. These are things that we're going to see when we're talking about logic. This little symbol here looks like we call it the caret. We normally use it in math to raise something to a power. That's a conjunction. That's basically an and, right? It's the word and. And if you think about it, it looks an awful lot like, remember this symbol, the round one, for the intersection of two sets? And this ended up being this, the stuff that was in both A and B. Remember the intersection? That's stuff that's in both. So there's a similarity between the symbols. So of course, this symbol, which means or, is very similar to the horseshoe, the U symbol. And that's called the disjunction, but who the heck cares? But remember, the or just represented everything. So the or would be all of it, all three pieces, right? That's or, and this one is and. And then not is a little tilde. That's called a tilde. That's a little squiggly symbol. And on your keyboards, it's over on the left-hand side next to the one, usually above the tab key. So that's the symbol that we'll use for a negation. It's kind of similar to a minus sign. So now with that being said, we can use these symbols to take kind of math speak and turn it into English if we let letters represent various statements. Again, remember things that can be true or false. So it is raining, sorry, it is raining is a statement because either it is or it isn't. Yes, I know it can rain and then stop raining, but at any one given point in time, it's either raining or it's not. So it's true or false. It can't be both. That's a statement, right? It is March, also always either true or false. And if we let P equal that and Q equal that, then P or Q just means it is raining or it is March. A negation basically just means we're going to take the opposite. So this negation sign basically corresponds to it is not the case that, right? That's the English version of the negation of something. So it is not the case that it is raining and it is March. All right, next example. Quantifiers. Some more definitions first. So we're going to have words that we're going to be using that we call them quantifiers because it basically tells us how much, right? Quantifier, quantity. So words like all, of course, means we have everything. Each, right? Individual things. Every is kind of like all. No or none. These are all what are called universal quantifiers. Because the reason why they're called universal is because they represent everything, right? All is all of it together. Each is the same thing, right? It's each thing, but it's still all of them. Every and no or none or none of them. So you see how those are like absolutes. While we have these other words, some, there exists, and for, and at least one, all of those things are existential quantifiers because they just give us a certain amount, something less than the extremes. It's not all and it's not none, but it's somewhere in between. Now, these quantifiers, we use them strictly to indicate how many cases of a certain situation we're talking about, or if we're trying to determine if something's true or false. We've already seen these words before in probability. We've seen at least one questions and stuff like that. So you're already familiar with them. Now, negations of some of these quantifiers. Remember we talked about the at least one and what the negation of that was? None of them. So we could even add that in to this list, right? We know that if the statement is at least one, we know the negation, the opposite of it, would be none. If we have the statement all do something, then the negation is just that some don't do it. And I know you're thinking that the negation of all do is all don't. But when we're talking about quantifiers, it goes from all to some, right? Some to none. Do you see how it goes from extreme to somewhere in between? Somewhere in between to extreme. So you can see you've got the two extremes here, all and none. And then the negations are some. So all do, some do not. If just some of them do it, then none of them do it, which is really the same thing as all do not. It just makes more sense to say none of them do something than to say all of them do not do it, right? But you can see the pattern, right? You go from do to do not, do to do not, and you go from all to some to all, right? It's just verbiage wise, it makes more sense to say none do than all do not. But that'll hopefully help you understand and kind of see the pattern. Here are some examples, right? Some cats have fleas. So remember, some goes to none, right? So some cats have fleas. No cats have fleas. Some cats do not have fleas. All cats have fleas. No cats have fleas goes to some cats have fleas, which, it's repeating itself. I mean, some cats have fleas goes to no, right? And then no cats have fleas goes to some. You go, well, duh. Of course they have to go back and forth. If one is the negation of something, then it's in the other direction, it's still a negation. All right, the last thing we want to talk about in this section are the different types of numbers. We have the natural numbers, which are also called the counting numbers, and those are just, if you wanted to start counting on your fingers, you would start with 1, right? You don't start with 0. So the natural numbers start at 1, and if you counted your fingers, 1, 2, 3, 4, 5, all the way up to 10, and you'd keep going. And those are the natural numbers. They're basically just the positive integers. Now, the whole numbers are just the natural numbers plus 0. That's all you're doing is you're adding 0 into that group of things. Set of things. Then the integers, you're just adding in all the negative numbers, right? So you have the counting numbers, 1, 2, 3, up to infinity. You have 0, which now makes the whole numbers. Then you add in the -1, -2, -3, down to negative infinity, and now you have the integers. So you can see each of those is just kind of building off the previous. It's just a bigger and bigger set. Then you get the rational numbers, which is an even bigger set, because rational numbers are all fractions, where p and q are integers. So anything that can be listed as p over q, where p and q are both integers, and of course q can't be 0, is considered a rational number. So 1/3, 1/2, 1/5, 2/3, 7/10, all those things are rational numbers. But here's the thing, so are all of the integers, because 1 is just 1 over 1, right? And 3 is just 3 over 1, and 0 is 0 over 1, and -7 is -7 over 1. So if you took any of the numbers from these three sets and just put them over 1, you've now turned them into a rational number. So all of these sets are actually contained inside the rationals, and now you can see that the rational is an even bigger set. So even though this set has infinitely many numbers, right, because it goes all the way up to infinity and all the way down to negative infinity, we can now see that this set is bigger. So there are actual degrees of infinity. There are larger versions of infinity, because it should be quite obvious to you guys that this set has more numbers, because it contains all of these, right? Because all of these can be listed as their number over 1, so they're all in this set. But this set also contains 1/2, 1/3, 5/2, 5/3, all those things that aren't in the other sets. So it's a bigger set. It's got more things, right? So there are degrees to infinity. Now, the irrationals are basically the negation of the rational. Anything that cannot be written as p over q is called an irrational. And again, the irrationals are in fact infinite. There are infinitely many of them. It is a smaller infinity, but there are infinitely many of them. In fact, I think there's an argument as to which one's bigger, but if I remember correctly, I'm pretty sure the irrationals have been proven to be smaller, but I could be wrong. But in any case, the irrationals are things that can't be written as a fraction. Stuff like pi, right? Pi is an irrational number because the digits go on and on forever. They never stop, and there's no repeating pattern, so you can't list it as a fraction. Same thing with E If you've ever seen, E for exponential functions, and E is roughly 2.71 blah blah, and it's just like pi. It goes on and on forever. Okay, and then we have the real numbers, which is the granddaddy of all sets. These are in a hierarchy basically. As you go down the list, the sets get bigger and bigger and bigger. Except for these two, they're negations of each other that make up the reals, right? The reals are split into two numbers, the rationals and the irrationals. So if you think about it, it's kind of like this big, huge set here, and over here are the irrationals, and over here are the rationals. And then within this, we have smaller and smaller groups. So within the rationals, we have this subset that are the integers, right? And then within the integers, we have this subset that are the whole numbers. And then within the whole numbers, we have this smaller subset that are the natural numbers. And this big ball on the outside, right, this big thing, is the reals. And the reals are, what we know. It's just all numbers that are all over the number line, all positive and negative numbers, whether they're fractions, decimals, whole numbers, irrationals, pi, e, all that stuff. The only thing that isn't in the real numbers are the imaginary numbers. And if you remember imaginary numbers from your old algebra class, imaginary numbers are things of the form a plus bi, where a and b are real numbers. And then I is that imaginary number, which is the square root of -1, which of course we know in the real world doesn't exist, but it does actually exist in electrical engineering and things like that. Okay, so last and final example. Decide whether each of the following statements about sets of numbers is true or false. Every integer is a natural number. True or false? Well, it's false, because if we go back here, every integer is not a natural number because we have all these negatives. And then there exists a whole number that is not a natural number. So do we have a whole number here that is not a natural number? And hopefully you're all saying yes, because we have 0, right? This is true because 0 is a whole number that is not a natural number. And that's it, guys. That's our introduction to statements and quantifiers.